Okay, let's continue the discussion. We talk about theorem 4.27. The inverse function theorem. Okay, so, wow, horrible. Okay, let f be one-to-one and continuous. On an open interval I. If A inside f of I and if f prime, the derivative of f evaluated at f inverse of A exists and is non-zero, then f inverse is differentiable at A and f inverse prime evaluated at A is equal to 1 over f prime of f inverse of A. Okay. Okay, so let's see the proof. This theorem just connected the derivatives of f inverse and f. They gave us a relation about them. And in fact, you can remember this or memorize this as a chain rule. You can memorize this as a chain rule. So check here. We know that f of f inverse of A of x is equal to x if they are both differentiable. I say if they are both differentiable, then by the chain rule we will have a differentiated external function evaluated at internal function, and you differentiated the internal function, it is equal to 1. And when this term is not equal to 0, you divide this equation by this f prime. You have that formula. So this is the argument when we study the calculus. When we study the calculus, we say if they are differentiable. And in this theorem, we just solidly show that it has to be differentiable, and we have such formula. Okay, it has to be differentiable. This is not part of an assumption. This is part of a conclusion. That's the difference between the calculus and the analysis. Okay, so we have one-to-one continuous function. Then by the previous theorem, by 4.26 just says if you have a continuous and a one-to-one function, then function has to be strictly monotone. So f is strictly monotone. It has to be either strictly increasing or strictly decreasing. In the book, they assume it's a strictly increasing. Here, let's just assume it's a strictly decreasing, the same thing. On this open interval I, and this time it's open interval. And And then we also know that by the same theorem, 4.26, f inverse is also continuous and strictly monotone, with the same monotonicity, increasing of f, then increasing of f inverse, decreasing of f, decreasing of f inverse. So f inverse exists. The existence of f inverse comes from 1 to 1. It does not come from other things. It's continuous. Continuity is proved. We did prove the continuity, and the proof is a little bit strange. We have to show that the right limit, left limit stuff, because we want to use the monotonicity. We do not directly show it is continuous. We use a two-sided limit, one-sided limit, and is strictly decreasing, because here f is assumes strictly decreasing, so f inverse is going to be strictly decreasing on f of I. Okay, so that's a general conclusion from the last theorem. Now let's pick up fixed point. We want to show the differentiability. So let x0 be f inverse of A, which belongs to I. So A belongs to Fi, then f inverse of A belongs to I. Okay, I is an open interval. You have a point inside it, so it means there are CD in I with x0 inside the open interval CD containing I. So there's small open interval including containing x0, containing x0. And we know that f is a continuous function, monotone continuous function. So by the intermediate value theorem, we can see that FCD, the image of this open interval, is equal to FD, FC, FD, FC. So this is done by the strictly decreasing property. In the textbook, this is FCFD because they assume it's strictly increasing. Here is we assume it's strictly decreasing, so we just modify this part. Okay, and this contains what? Contains point fx0. Contains fx0 is A. Fx0 is A. So A is inside this open interval. A is inside open interval, then for h not equal to 0 and sufficiently small, A plus h will belong to FD FC. A plus h belong to FDFC, and F inverse of A plus h is well defined. F inverse of A plus h is well defined for whatever h non-zero and sufficiently small. Well, when we say sufficiently small, you can just get h0, when h is always less than h0, then this is well defined. That's what we say, sufficiently small. All right, okay. Okay, now let x be f inverse of A plus h. X is a f inverse of A plus h. It's a moving point. It's a moving point with respect to h. Then fx is A plus h. Where is it? A is fx0 plus h. Right? So we just get the relation. So what we have h is equal to h is equal to fx minus fx0, fx minus fx0, like this. Okay, so let's see. F is continuous. F is continuous. So x approaches x0. When x is close to x0, it implies difference is small. This implies h approaches 0. F is continuous. It implies h approaches 0. And let's see this. X minus x0. X minus x0. X is a f inverse of a plus h. x0 is f inverse of a. F inverse of a. Right? This x minus x0. So we know f inverse is continuous. When h, so it implies h approaches 0, implies x minus x0 approach 0. So x approaches x0. When h approaches 0, f inverse is continuous. So it implies this difference approaches 0, so x approaches x0. And we know f and f inverse are both continuous, so these two conditions are equivalent. Hence, x approaches 0 is equivalent to h approaches 0. X approaches 0 is equivalent to h approaches 0. All right, so that's because of these two continuity. Now let's try to compute the derivative. We're talking about the differentiability. Now let's see what is the derivative. Derivative, we're talking about the derivative of f inverse. So this is the derivative of f inverse. F inverse of a plus h, f inverse of a plus h is x. F inverse of a is f inverse of a is x0. H, where's h? H is f x minus fx0. See, we just transform from a and h to x and x0. And of course, we flip this to the denominator. And remember that x approaches 0 is equivalent to h approach. X approaches x0 is equivalent to h approaches 0. So if we put limit h approaches 0, f inverse a plus h minus f inverse of a over h, you can just put limit x approaches x0 1 over fx minus fx0 over x minus x0. Right? So that's that is the place where you use this condition. And we know this one, the limit exists because f is differentiable. So it is equal, the numerator has limit because it's constant. So it is equal to f prime of x0. What is f prime of x0? x0 is here, so it is equal to 1 over f prime of f inverse of a. And this is exactly the f inverse prime of a. So we have it. Okay? So we check the proof. We check the proof. All right, so we get the derivative of f inverse in terms of the derivative of f, but with the evaluation at different point. Here you evaluate at a, here you evaluate at f inverse of a. Okay. So, very good. Now let's see a little bit. You see that we had, we had a function like that, f of x. We just talk about the 0, 1. It is 0 and 1 if x is whatever way, irrational, and x is rational. And then this function has no limit or no one-sided limit at all. No limit, no one-sided limit at all. It's a very bad. Right? It's not continuous at any point, no limit. No one-sided limit at all. But this function is not monotone function. And we want to claim that if we have a monotone function, then this horrible situation will not happen. This is a horrible situation, okay? So, we first see this lemma. Suppose that f is increasing on AB. Here, increasing, you can replace it by decreasing with a similar proof. You're going to do that one, okay? You're going to change f to be decreasing and go through the whole proof. But of course, when it's decreasing, the conclusion will be should be modified. Okay, let's see what we're going to say. If x0 belongs to the A closed A open B, okay, we are including the left hand point but excluding the right hand point. Then f x0 plus the right hand limit always exists. Right hand limit always exists. Because when x0 is b, is the right hand limit, there's no right hand side. So that's why we exclude the right hand limit. And fx0 is less than or equal to fx0 plus. The right hand limit is always greater than or equal to the value. Okay, so the first conclusion, this less than or equal to condition, the inequality, is related to increasing. Is related to increasing. If this place you change it to be decreasing, then this part you have to change it to be greater than or equal to. Okay, but the existence does not change. You always have exist. The one side limit exists. Okay, so that's what I say. If you change this f to be decreasing, then this is a greater than or equal to. If it's increasing, it's less than or equal to. You try to do the proof, see if you handle the whole idea. And if x0 belongs to open A closed B, then fx0 negative plus minus fx minus, this is a left hand limit. Left hand limit cannot be defined at the left hand point, so we exclude the left hand. So this exists. And fx0 minus is less than or equal to fx0. The same thing, if it's decreasing, you are going to change it to be greater than or equal to. Okay, so increasing is always less than, less than, less than. Decreasing it will be greater than, greater than, greater. All right, but here, same thing. Right hand limit, left hand limit, both exist for increasing and decreasing case. But those two limits may be different. We just say if you have a monotone function, it may not be continuous, but at least one side limit exists. All right, so let's see how do we prove it. Let's see how do we prove it. So proof. Fix x0 inside A close to B. They choose this one. It doesn't matter which one you choose, it's the same thing. So by symmetry, it suffices to show that fx0 minus exists and satisfy fx0 minus less than or equal to fx0. Okay. Well, let's see. We're talking about the left limit, so x is on the left side of x0, x is less than x0. So set E to be the set fx a is less greater than a is less than x0. We're talking about the left limit, left hand limit or left side limit, and let S be the supremum of the set E. It is supremum of the set E. Okay, a function is increasing. A function is increasing, so fx0 is an upper bound. Upper bound of E. fx0 is an upper bound of E. Hence, S is finite. S is finite. S will not be infinity. And S less than or equal to fx0. Less than or equal to fx0. Alright. Now we're going to show that this S is exactly, we show that this S is going to be fx0 minus. How do we show it? How do we show it? For every epsilon there's a delta, so that when x is x minus x0 is less is greater than delta. Okay, so for given epsilon greater than 0, we want to find the delta greater than 0 such that x0 minus x is greater than delta, less than delta, it's positive, greater than 0, less than delta. Very close. No, x minus x0 less than negative delta. Greater than negative delta, less than 0. The left side. Less than 0 greater than negative delta implies fx minus minus s ups value is less than epsilon minus s. So we're going to show this. Okay, so how do we do that? Given epsilon greater than 0, then by the approximation property, what is approximation property? Approximation property is about the supremum. By the approximation property, there is an x1 belong to ax0 such that fx1 is less than or equal to s but strictly greater than s minus epsilon. So it's very close to this supremum. Very close to the supremum. And here is the reason we use this part instead of the other one, the first part. The reason is that the approximation property literally from the theorem, this approximation property is state for the supermom. If you want to prove part 1, you're going to use infimum instead of supermom. But for the infimum, strictly speaking, we don't have we have some similar approximation property, but it's not listed in the textbook. So that's why the author tried to just use approximation property word by word from the textbook, not from some extended version of approximation property. Of course, in the infimum part, we have infimum version of approximation property, definitely, okay? But here, let's just follow the textbook word by word so that the approximation property corresponds to the supermom, and slightly smaller than supermom. There's always x1 so that the value is greater than it, okay? Okay, so f is increasing. So for whatever x between x1 and x0, s minus epsilon less than fx1 increasing, okay, could be equal, right? Because s is supermom, so definitely it's less than or equal to s. So we want to control this. All right. So what we get? We get to choose delta be x0 minus x1. x0 is greater than x1. Positive. For whatever x minus x0 less than 0 but greater than negative delta, that's x. We have fx minus s is greater than epsilon, negative epsilon, so put up's value is less than epsilon. So s is the fx0 minus the left hand limit. And of course, s, remember here, s is less than fx0. Okay, so this is the proof. We prove this, and by symmetry we can show the right hand limit, left hand limit. They're almost the same thing. Again, why we choose the proof of second part instead of the first part? Just because for the second part you have the supermom. For the supermom, you have the approximation property listed as a property in the textbook. Okay, that's the only reason we selected the second part to show it. If you have a decreasing version, definitely you will prove the first part because it's greater than or equal to. Remember, whenever you have greater than or equal to, that you will use the supermom instead of infimum. All right. So what we have from this lemma, we just showed that if you have a monotone function, forget about the continuity. At least for every point, one-sided limit always exists. If for every point one-sided limit exists, the discontinuity can be at most a jump. So it can be at most like this. There's no horrible situation, but just like this, there's a jump at most. Okay. Now let's continue this discussion and talk about discontinuity. Theorem 4.29. If f is monotone on an interval I, then f has at the most countably many points of discontinuity. On I. Countably many points of discontinuity on I. Alright? Countably many. So what this mean? Here, this one, every point will be a discontinuous point. So it has uncountably discontinuous point. So to be the horrible side, a function may have uncountably many discontinuous points. But the theorem 4.29 will claim that if you have a monotone function, you can have at most countably many points of a discontinuity. Countably many and uncountably many, there's big difference. Okay, there's a big difference. So we will see that a monotone function will be relatively good. Relatively good. Okay. Monotone will have increasing, decreasing. So without loss of generality, we assume that f is increasing. F is increasing. Okay, and we know one property. We know that the countable union of at most countable sets is countable. Countable union of at most countable sets is countable. At most means it could be finite, it could be countable, right? At most. Okay, so in order to show that the set, the points of discontinuity, the set of the points of a discontinuity is countable, we are going to write it as a countable union of at most countable sets. Okay, so that's what I say. It suffices to show that it suffices to show that the set of points of discontinuity of f can be written as a countable union of at most countable sets. Okay. Okay. So that's how what we're going to prove. That's what we're going to prove. Remember that what I comment. If you have a monotone function, the left limit, right limit exists. So the gap is the discontinuous type is just to have a jump. So left limit does not match to the right limit, then there's the discontinuous point. Okay. That's an observation we need to keep in mind. Okay. let's see. We are going to first we write the R as the union of R as the union of a negative n to positive n, negative n to positive n. This is a countable union. Remember, this is a countable union. It's a countable union, and this hypothesis, we just say an interval I. Interval, we don't know it's open or closed. Let's just assume I is assume. Let's assume that I is a closed bounded interval AB. Why can't we assume it's a bounded closed interval? This I could be from negative infinity to positive infinity, the whole real line. It's okay. But we always use this closed interval, negative n, positive n, to intersect I. So actually, if you have a general I, you get intersection. So then you will always have a bounded set, and you can call this I sub n. And then you get I to be the union of all I sub n. It's a countable union. Be careful. Here's a countable union. And if we can show over each I, f has at most countably many points of a discontinuity, then put union together, you still have at most countably many points of discontinuity. So it does not violate the whole proof. So that's why we assume we can assume here is closed, so we just use a closed set to cut it. So that's why we can assume it's closed and bounded. Otherwise, the theorem works for all types of I, bounded or unbounded. It's not necessarily just bounded. Okay? Okay, so now let E represent the set of points of discontinuity of f on the open interval AB. Just two endpoints, it doesn't matter. We don't care the discontinuity. We add those two endpoints or not, doesn't matter. Okay, so all the set point of discontinuity. And we know that the previous lemma, we know by lemma 4.28, just previous lemma, we know the left limit is less than or equal to fx, less than or equal to the right limit. Be careful here, we assume it's increasing, so we can directly use it. If it's decreasing, we have similar one, but change the direction. Okay? Change the direction. And then we see that the f is discontinuous at x if and only if fx plus minus fx minus is strictly greater than 0. When there's a gap, those two one-side limit do not match, then you have a discontinuous point. Okay? Okay, so we let aj be the point in where in I with fx plus minus fx minus greater than or equal to 1 over j. any smaller number. This time we use 1 over j to represent a smaller number. And then aj is a subset. Aj is a subset of points of discontinuity. Because every point here, every point inside aj will be discontinuous, a point of discontinuity. And we say E represents all of them. So E is equal to the union of AJ, J from 1 to infinity. J is from 1 to infinity. Okay, so if we can show AJ is at most countable, then E is at most countable. E is at most countable, then we can see that I sub n is at most countable, and then you union them, you will get I is at most countable. But in fact, we're going to show that AJ is finite, even stronger. At most countable is enough, but this is finite in fact. Finite is also at most countable, right? We will show that AJ is finite. Let's prove if not for all j. If not, there is an j sub 0 such that aj sub 0 is infinite. aj sub 0 is infinite. aj sub 0 is infinite, then let's see. We can pick up infinite, we can always pick up. Not all of them, but just pick up x1 less than x2 less than x3 less than in aj sub 0. aj sub 0. This is infinite. With what? Because they are all inside aj sub 0, so fx1 plus minus fx1 minus, this is greater than 1 over j sub 0. 1 over j sub 0. And actually, let's put k. F of xk plus minus f of xk minus for all k. Okay, let's check. Let's check what contradiction we will have. And a sub j is inside I, so it's bounded by a and b. It's bounded by a and b. There's no include. So if we put fb minus fa, fb minus fa, we can write something like this. Fa and fx what we can write. I'm trying to get some hold on a second. How do I okay, this way, let's see how do we do it. This is stupid. FB, this place we use minus minus fx1 plus fx1 minus fa see it's the same thing. And remember this condition. We have this condition always. So I'm going to subtract the big. Subtract the big. Fx1 plus. Add smaller, this one smaller. Right? Add smaller, so it's greater than. It's greater than it. Subtract the more, add less. This is okay, it should be well, it's not this way. It should be the following way. Let's see. So f is increasing. F is increasing. This fa is here. See here, a is less than x1. Fa will be less than fx1, and fa is actually less than or equal to fx1 left. So with the minus, it's greater than or equal to. And fb similarly is greater than or equal to fx1 plus. Okay, so this one is greater than 1 over j0. That's one step. And then let's continue this. Here, we do not replace x1 plus. We put fb is actually greater than or equal to fx2 plus. This is one possible way. So fb is greater than or equal to fx2 plus and minus fx1. And then I'm going to insert fx2 plus, fx2 minus, and plus fx2 minus, minus fx1 minus. We insert it. And then this one, fx2 minus is greater than or equal to fx1 plus. Fx2 minus is greater than or equal to fx1 plus. So the thing is the following. This is A, this is B. It's increasing, so A is here, B is here. At a point of discontinuous point, so the graph will reach here, and this graph will reach here. This is a gap. This gap is 1 over j sub 0. At another point, this gap is greater than 1 over j0. So you add all these gaps together, it should be less than or equal to the total gap between fa and fb. Fa and fb. So that is the geometric observation. And here, because it approaches x, this is x2, this is x1. So naturally, the left-hand limit at x2 should be higher than the right-hand limit at x1. So that's why we have this conclusion. So it's greater than or equal to fx2 plus minus fx2 minus plus fx1 plus minus fx1 minus. And this becomes 2 over j sub 0. And you can, of course, start from here. And you replace fx2 by fx3. Then you will get a 3 over j sub 0. So eventually you can see that it will be greater than or equal to n over j0 for all n, for all integer n. This will imply fb minus fa is infinity. Okay, it has to be infinite, but this is impossible, a contradiction. Therefore, you cannot have infinitely many, so aj sub aj must be finite. Aj must be finite. Okay, so that's the conclusion. Aj is finite, then E is finite. E is a finite, then I has a finite, countably many. Aj is finite. E is at most countable, and F will have at most countably many points of discontinuity. All right, so that's that stuff. Okay, we still have one more theorem. We will leave it to the next video. Okay, thank you very much, and try to understand this part. Okay, thanks.